I gotta throw something in before I post the video here, and that's to say that I got the gender of Fotini Marco Polo incorrect. Fotini is a female. I consistently refer to her as a male in this video, but I don't want to remake a 10-minute long video. So, just to note, I do realize that Fotini is a female now. For some reason, maybe it was just when I was recording, I decided to refer to her as a him. So, my apologies. Anyway, continue on with the video. Good morning, everybody. I felt the urge to make a new video. What I had been doing for the past week or so, aside from the rest of my life, was taking a look at some debate between Lawrence Krauss and William Lane Craig, discussing the universe needing a cause for its existence. And Lawrence Krauss is of the opinion that the universe came from nothing, and Craig seems to think that the universe needs to have a cause, a personal agent, aka God, making the universe. And when they two debated, there were a lot of terms being thrown around that weren't very well clarified. It was kind of assumed the audience understood what was meant by nothing, beginning, time, etc. And Craig took these to what would be a logical conclusion if those were the case. However, this is not the case. And what I want to do today is just define these terms of beginning, nothing, and time, and what it means to a physicist when they actually are talking and using these terms. Because to a layman, they seem to apply one thing, but from what the physicists actually write in the literature, it actually says something totally different. And we'll see that Craig's conclusions aren't really warranted from these definitions. So let's begin by trying to define nothing. It doesn't sound like a very difficult task. If we have nothing, there we are. There's nothing, there's no space, no time, no whatever. However, if we take a look at Vilenkin's paper, he defines nothing a little more clearly for us. And he's the physicist who Craig liked to use in the debate with Lawrence Krauss, and he said that Lawrence Krauss was misinterpreting Vilenkin and that Craig had the proper interpretation. And I guess we'll see how true that is by reading Vilenkin's work. He writes in 1983, in his paper, The Spontaneous Creation of Universes, whereby nothing, there's talking about nothing here, whereby nothing I mean a state with no classical space-time. Nothing is a realm of unrestrained quantum gravity. It is a pre-geometric state in which all of our basic notions of space, time, energy, entropy, etc. lose their meaning. So, all of a sudden, nothing is very much something. Nothing is a very different definition than what is intuitive. So, if we go back to what Craig was using in his argument, the Borde-Guth-Vilenkin theorem, it shows that classical space-time, aka what we know from relativity, coupled with inflation, cannot be eternal into the past. If we follow it backwards long enough, there's going to be a boundary. It's going to stop somewhere. So it must have had a beginning. That's perfectly fine. Yet before this beginning, before it, whatever before means now because we lose our sense of time, the universe is still described by quantum gravitational processes, as evidenced by Vilenkin himself in his own work. This is a very physical, if not difficult to understand idea. So again, if we start with our current universe and work our way backwards, we slowly have our other fundamental forces being unified, our weak and strong nuclear force, our electromagnetic force, and then we go back even further, where gravity needs to be unified in a theory of quantum gravity, and suddenly we lose our notion of space and time as well. It kind of disintegrates. And we're left with a universe with only quantized space and time, which lacks the here, there, now, and later that we're so used to. And in fact, the process by which we can go from quantized space and time to our current notion of space and time has a name, geometrogenesis, and it's the attempt to understand how this can actually work. Now, the details are way beyond the mathematics that I ever learned as an undergrad. However, the idea can be thought of kind of like this. When you take a glass of water and you put it in your freezer, at a certain point, the water is going to freeze. This is what's known as a phase transition, where the structure of the water is going to fundamentally change at a certain temperature, all of a sudden. And that seems to be the idea with space-time and geometrogenesis. So if you have your quantized space-time at a certain energy, you suddenly get to continuous space and time, the one that we know and love today from relativity. So this suddenly gives us a new definition for what beginning means. It's not the beginning that William Lane Craig seems to think it is, where it suddenly requires us to have an agent making it happen. The beginning just means a transition from this quantized space-time to a classical space-time, the space-time that we know today. Of course, how does this transition take place if transition is a temporal thing and suddenly we don't have time? So Fontini Marco Polo, in his paper Space Does Not Exist, So Time Can, gives us one possible solution. And I'm going to quote this whole thing, and keep in mind, this is just one possible solution. Other people believe that space and time both are not fundamental. But Marco Polo seems to think time is fundamental, but that it has a sort of emergent time property that we'll see. So he writes, let us call the first geometric time and the second fundamental time. In our geometrogenesis context, it is clear that the geometric time will only appear at low energy when geometry appears. This is our phase transition, by the way. Continuing on, the problem of the emergence of geometric time is the same as the problem of the emergence of space, of geometry. When people say time does not exist, they refer to geometric time. By making the geometry not fundamental, we are able to make a distinction between the geometric and the fundamental time, which opens up the possibility that, while the geometric time is a symmetry, the fundamental time is real. By distinguishing the two notions of time, we may be able to have our cake and eat it. Emerging geometric time from fundamental time is not remotely as intractable as dealing with a fully timeless world. Now, the reason I chose that was because that one made a lot more sense to me. There are other ideas that do involve space and time, both not being a fundamental quantity. But how those things evolve, how a wave function, for instance, would evolve to suddenly collapse and lead to our continuous space-time, I just couldn't explain it. It didn't make any sense to me. It could very well be correct, and I've learned from taking a year of quantum mechanics at my undergrad that just because I don't get it doesn't mean it ain't right. So that's okay. I mean, these are plausible explanations for how time could have arisen due to totally physical processes, not requiring a causal agent that Craig will want, and we'll see that in just a second. So in fact, I'm just going to end this video now on a note about the Craig-Krauss debate, and moreover what Craig writes about the cosmological argument on his own blog here. So he writes on his website, which is reasonablefaith.org, in an article titled The Existence of God and the Beginning of the Universe. He says, in conclusion, we have seen on the basis of both philosophical argument and scientific confirmation that it is plausible that the universe began to exist. So far, so good. Given the intuitively obvious principle that whatever begins to exist has a cause of its existence, we have been led to conclude that the universe has a cause of its existence. On the basis of our argument, this cause would have to be uncaused, eternal, changeless, timeless, and immaterial. Moreover, it would have to be a personal agent who freely elects to create an effect, in time. Therefore, on the basis of the Kalam cosmological argument, I conclude that it is rational to believe that God exists. Okay, so about halfway through, we suddenly see this conflation of terms of the universe begins to exist. Well, what does beginning mean? Beginning means, at least in Marco Polo's interpretation, it means the beginning of classical space-time. Actually, in all the definitions, it means the beginning of classical space-time. That's what the BGV theorem proved, that classical space-time has a beginning here. However, Craig goes on to say that this means it's uncaused, eternal, changeless, timeless, and immaterial. Well, we've seen that's not necessarily the case. Marco Polo tells us, in his work at least, that time can have two different, very distinct definitions, and that the only time that began to exist is geometric time. So when we say it's timeless, that doesn't mean there's no time in a different sense. There's just no time in the classical space-time sense that we know. And the same thing goes with space. But the most important thing to notice here is that there's no warranting of getting an uncaused agent, some being who thinks things into existence. If we go back all the way using physics, we still get more physics. The physical laws still exist. We can get this universe from nothing, but we really have to be careful about what we know nothing means. Nothing doesn't mean what William Lane Craig here seems to think it means. It's still a very physical, a very real thing, just very counterintuitive. And I hope that, I guess, clarifies or somewhat clarifies. I know it doesn't do it any justice right now because it's such a broad field. But I hope this gives a little bit of clarification as to what we should think of when we hear physicists talking about nothing, because it definitely is not the nothing that we think it should be. So I hope that wasn't too confusing of a video. I hope you learned a little something. And if you want me to clarify more, let me know in the description and some comments, and I will do my best to try to clarify it for you further. And I'll be making a video shortly about the BGV theorem itself, because Craig seems to love to use that one. And we'll see what the theorem actually predicts and why it's not quite what Craig seemed to think it is. Alright, so take care, and I'll be making a video shortly. See you guys. Bye.